align best with rational functions, but there are obviously connections to other things we're going to do in this course and kind of beyond. So kind of keep it more general there. And you do notice I have Desmos up on the side. This is just to kind of see what's happening on the graph rather than just talk about it. So big idea here is just going to be undefined values don't disappear. On the graph, they're going to show up as missing x values. Now for the rational functions, that's going to be as vertical asymptotes or sometimes wholes. Other functions, they will do other things, but they don't just disappear. It's not just x can't be this, the end. So let's dive in. So a hook is going to be, if we have a function f of x, if f of x becomes 0, kind of ask yourself what is happening to 1 over f of x. And then flip side, if a factor cancels, right? So if whatever made f of x 0 can be divided out, is that restriction truly gone? Do we have to worry about it or not? So to kind of address the first part of the hook, let's look at the function g of x equals 1 over x minus 3. So this is the function 1 over f of x, right? So if I look at this, I can kind of see this x minus 3 is the f of x part. So f of x here is x minus 3. So, well, what happens when f of x equals 0? So f of x equals 0 is really just x minus 3 equals 0. Sorry, f of x equals 0 is x minus 3 equals 0. So then we know x is going to be 3. So that's going to be our non-permissible value. So as I look at that, we know x equals 3 is in the denominator. So our question is, what's happened to our graph around x equals 3? So we have a non-permissible value. X cannot be 3. What's happening near 3? So we could approach this a couple ways. We could say, first of all, we could just write domain. We kind of know, okay, domain is going to be x is an element of the reals. X can't be 3. Another way to write that is x is anything up to 3 or anything above 3. That's also fine. So algebraic, we can kind of look at this. We could say, well, what happens as x approaches 3 from the right? What if we're a little bit bigger than 3? So i.e. like 3.1. Well, if x is 3.1, g of 3.1 is going to be 1 over 3.1 minus 3, which is 0.1, which would give us 10. Or what if x approaches 3 from the left? Well, if x approaches 3 from the left, like 2.9, g of 2.9 is going to be 1 over 2.9 minus 3, negative 0.1, which is negative 10. So we can kind of see from the right, it looks like we're getting pretty big, and from the left, we're getting pretty small. But let's just look at a graph. So on the graph, you can see I have g of x is 1 over x minus 3, and the line x equals 3. So if I look at that, this is what we see. And this does line up with what we just kind of recorded. So we can kind of see, well, okay, so as I approach from the right, I can see I'm going to get really, really, really big. And as I approach from the left, I'm going to get really, really, really negative, really small. And those are behaviors. So we can see that restriction x equals 3, well, it's just a non-permissible value, right? X cannot be 3. That was essentially what we wrote down. But we see it's actually a massive detail on the graph, right? It's a wall. So on the graph, it's a vertical asymptote. We can say the 0 of the original function, that f of x, the 0, becomes the wall of the reciprocal graph. It becomes an asymptote which won't be crossed, right? So you can see the graph can't be 3 and also acts really strangely around 3. So with that, let's turn that graph back off. And now let's go to your turn. So I'm going to give you a quadratic. So our question is going to be h of x equals 1 over x squared minus 4. I'm going to get you to identify the non-permissible values, predict the vertical asymptotes. And again, you're going to ask yourself, what's happening as your denominator gets really close to 0? So pause it, take a shot, and we'll pick it back up. Okay. So hopefully you had a few minutes to try it there. Just kind of that familiar structure. Again, we see that denominator. We can find the zeros of that quadratic pretty easily at plus and minus 2. Now, at those values, we're going to get h of x equals 1 over 0, which is going to leave us with a vertical asymptote at -2 and at +2. And pulling up Desmos, here's h of x. And I'm just going to label those asymptotes for us in orange again. And that's the graph you can see there. So this graph is kind of different looking, but the big thing is you can see those non-permissible values. So what we would say here, if I went back to the original question, we'd say, hey, x can't be plus and minus 2, but those non-permissible values have a big impact on the shape. Those really change the shape, as opposed to if we're kind of thinking that original function, the bottom, x squared minus 4, looks very, very different than what h of x looks like because of those asymptotes, because of those walls. And that's one for you to look at. So again, same idea, but a very different result. Okay, I'm going to do one more here. So I got, well, what happens if what happens if it cleans up? So we have r of x equals x minus 2 over x plus 1 over x minus 2 times x minus 3. So again, same idea, state the non-permissible values, simplify, and identify the graph behavior at those restricted values. Okay, so as I go at this question, I'm going to say, well, right away, this is already factored for me, which is nice. So I know my non-permissible values. My non-permissible values are going to be anywhere the denominator equals 0. Denominator equals 0. So this is x minus 2 times x minus 3 equals 0. So I can see that's going to happen when x is 2 or x is 3. So those are the non-permissible values, x equals 2, x equals 3. So I could say that non-permissible values, 1, 2. So therefore what that's saying is the domain is going to be x is an element of the reals, x cannot be 2 or 3. And again, we could write that everything up to 2, everything between 2 and 3, everything above 3. Either way, that's fine. So x cannot be 2 or 3. Okay, now let's simplify. Well, so r of x, we know is x minus 2, x plus 1, over x minus 2, x minus 3. But really, if we saw this, we would immediately say, well, x minus 2 divides out, which leaves the r of x equals x plus 1 over x minus 3. But our question is, does our function have a memory of that x minus 2, right? Because we can look at this. We know obviously x can't be 3, but do we need to keep writing x can't be 2? So this is our kind of question, like, do we need to keep writing that? And let's just look at the graph. Let's look at the graph to see what happens. So if I pull up the graph, turn these off. So here's r of x, and here's that point, 2, x equals 2. So if I look at this does look pretty normal. You can see there is an asymptote at x equals 3. It's not labeled here, but you can see it is at x equals 3. There's going to be that vertical asymptote, that wall. But what about the other one? So what about the 2? So if I plugged in, I'll go in purple here. If I went to plug in, so let's just check those non-permissible values. So if I plugged in 3, I get 3 plus 1 is 4 over 3 minus 3 is 0. That's the vertical asymptote. So vertical asymptote, we can see we get some number that's not 0 over 0. But what about if I plugged in the 2? Well, if I plugged in the 2, what I'm going to get is 2 plus 1 is 3 over 2 minus 3 is negative 1. So r of 2 is negative 3. And that looks okay. That looks like the point 2, negative 3. But as you can see on the graph, that's an empty point. The function actually doesn't exist there, because if we had gone back to the original, r of 2 we had the 3 over the negative 1, but really, remember, we also divided out the factor x minus 2. So we had 0 times 3 over 0 times negative 1, which is going to be 0 over 0, which is weird, and we say that's a hole in our graph, right? So that's a removable point. That's a point of discontinuity. It's a hole. And this goes back to a prior video. You do have to keep the memory. Yes, you do have to keep that 2 in your restrictions, because even though this was our middle step, so this is our middle, r of x, that simplified version, x plus 1 over x minus 3, 2 is still problematic for that function because the original function had 2 as being problematic. So that's it. You can kind of see the hole there. And if anything, in those restrictions, 2 is the more important restriction to note, because we should be able to look at this and say, well, clearly x equals 3 is going to be a problem. But if you had just been given this kind of middle, the simplified function, you would have no idea that 2 was a problem. So this graph kind of nice to show us. So our final checklist for us as we kind of work through these, is going to be look at that original denominator first. You can set the denominator equal to 0, and then you just solve with your existing linear quadratic skills. Keep those non-permissible values even after simplifying, especially after simplifying, because again, that kind of dividing out, you might say canceling, dividing out to 1 is not erasing history. So restrictions are set by the original denominator before any simplifying happened. If that factor did divide out, if it did cancel out, it becomes a whole, a point of discontinuity in the graph. If that restricted factor remains in the denominator, it is a vertical asymptote. So for you, you can kind of write a way to remind that for yourself. But that's going to be it for this video. Thanks for watching.